Let's practice naming alkynes. Our first job is to locate the longest carbon chain that contains the carbon-carbon triple bond and number that chain so that the triple bond gets the smallest possible set of numbers. At this point, we're not concerned about the numbering of any substituents that might be present. We're only concerned about giving the triple bond the smallest possible number. Right now, I want to take a little bit of a pause and talk about the way that we represent alkynes in line structures. The carbon atoms on either end of a triple bond are sp hybrid, which means that they have a 180-degree bond angle. And chemists usually try to reflect that by drawing a straight connection, 180-degree connection, between any single bonds that are up against a triple bond or any substituents that might be present on the other end of a triple bond. So this is why you see the drawing with this bond straightened out. We don't typically represent it like this with a bend at that because we're trying to show the 180-degree bond angle on either ends of the triple bond. So once we get our carbon chain numbered, we're going to go ahead and locate and name any substituents that might be present. We'll be doing that in alphabetical order, just like usual. And then we will give the location of the triple bond using the lowest numbered carbon of the two carbons in the alkyne. So this particular alkyne is going from carbon number 1 to carbon number 2, so we use number 1 as its location. And then we'll say the name of the parent chain, changing the ending of the name from ane to yne, Y-N-E. That's our notation to let us know that there's a triple bond present. And then the alternative numbering system allows you to put the location of the triple bond in the middle of the parent chain name. So hex 1-yne or 1-hexyne, whichever you would prefer. So this is just like with an alkene. Let's practice with these alkynes down here. First, I'm going to be finding the longest carbon chain that contains the triple bond, and it's going to be right here, like this. Now, because of the way that we represent the carbons in a triple bond, it can be sometimes easy to lose some of the carbon atoms. So maybe you want to put some dots or something to help you locate all of the carbon atoms in the line structure. We're going to number this one from right to left because our goal is to give the triple bond the smallest possible number. Our substituent is on carbon number 3 and it is chloro. And then we have our triple bond on carbon number 1 and this is a prop. 3-carbon chain is a prop, so this is a propyne. Or you could say 3-chloro-prop-1-yne. Here's our next example. This is our longest carbon chain, and our carbon atoms are located right here. We want to number from left to right. This is a 5, there's no substituents. It's a 5-carbon chain with the triple bond on carbon number 2, so we would call this 2-pentyne, or if you want to see it the other way, I usually don't like to use the numbers on the inside of the carbon chain, pent-2-yne. Here's our next example. This is our longest carbon chain is going to go right here, right through the middle of the molecule. That's a 1, 2, 3, 4, 5, 6 carbon chain. Whether we number from left to right or right to left, our carbon-carbon triple bond is going to be between carbons 3 and 4. If we went the other way, 1, 2, 3, 4. So we've got 4 methyl groups on this one. It's a methyl group on 2 and another methyl group on 2, a methyl group on 5 and another methyl group on 5. 4 methyl groups would be tetramethyl. Tetra isn't a prefix that we use very often. And our triple bond is on carbon number 3. This is a 6-carbon chain, so this is hexyne. Now here's one that is a little bit tricky. We've got a ring that has got 6 carbons in the ring, but remember our goal is to find the longest chain of carbon atoms that contains the triple bond. So even though this 6-carbon ring is the longest chain of carbons in the molecule, it's not going to be the parent chain when we name this molecule. This is our parent chain right here. And we're going to have to name this ring as a substituent on the parent chain. This is a concept that confuses a lot of students, not necessarily, students typically understand the idea that you need to find a chain that contains the triple bond. That part of it makes sense. But a lot of times when our parent chain has a cyclic substituent on it, people aren't quite sure how far that parent chain should go. Like, should we include this carbon atom as part of the parent chain as well? The answer to that is no. When you are choosing a parent chain, every carbon atom either needs to be part of a ring or needs to have nothing to do with a ring at all. So your parent chain either needs to be exclusively carbon atoms that are not in the ring or exclusively carbon atoms that are in the ring. You can't mix and match. You can't have some carbon atoms in the ring plus an extra bonus outside of the ring, or carbon atoms outside of the ring plus an extra bonus one in the ring. You got to go one way or the other. So this is going to be our parent chain, and we want to number it to give that triple bond the smallest possible number. Our substituent is on carbon number 1, and our substituent is a cyclohexyl. Cyclohexane would be the independent molecule in itself, and as a substituent, we change the ane ending to -il. That lets us know it's a substituent. And then our triple bond is on carbon number 2, and this is a 5-carbon chain, which is a pentyne. Now, one thing that we're going to talk about that's kind of funky, it is possible for you to end up with a molecule that has both a double bond and a triple bond, so it would be an alkene with an alkyne. And when we're naming this situation where we've got two functional groups present, it does get a little bit complicated. If we have both an alkene and an alkyne, the double bond gets numbering priority. So that means that our goal is to name the molecule as an alkyne, locate the longest carbon chain, and number it so that the double bond gets the smallest possible number. So let's just take a look at that piece right here. For this molecule, here is our longest carbon chain, and our goal is to give the double bond the smallest possible number. So if we go from left to right, it's going to be on number 3. If we go from right to left, it's going to be on number 5. So we would want to number this in this way. Now, again, this is because the double bond has priority. It's more important than the triple bond, so it gets the smaller number. The functional group name is ene-ine, alkene, alkyne, with ene coming first because of alphabetization of the ene and the ine. So when we name this molecule, we're going to change the ending of the name. We're going to drop the ane part and replace it with ene-ine. One of the tricky things is that we have to locate the position of the ene, and we also have to locate the position of the ine. And so this is an example where it's really handy to be putting the numbers in the middle of the name like I showed you up here. So for this one right here, I've already got it numbered. We can see that there's a methyl group on carbon number 2. It's a 7-carbon chain. Our double bond is on carbon number 3, and so I'm calling this a 3-ene. And our triple bond is on carbon number 5, so I'm calling this a 5-ine, and it does have the trans stereochemistry at the double bond. Now you'll notice here that this is not a typo, so it is not ENE. Typically alkenes, we would say hept. Normally we would say heptene with an E on the end right there. That final E is reserved for the very end of the name. So if you've got a functional group that is showing up not exactly at the very end of the name, it's not going to get that last E on it. It's saved for the very end. So let's try with this molecule right here. We want to find our longest continuous chain of carbon atoms, and it's going to be right there. That long chain needs to contain both the double and triple bond, and we want to number to give the double bond the smallest possible number. We have, I'm going to save stereochemistry for last. We have a methyl substituent on carbon number 2, so that's going to be 2-methyl. This is a 5-carbon chain, so it's going to be pent. We're going to name our double bond first, 1-ene, and then we'll name our triple bond next, 4-ine, give it that terminal E at the end. And then last but not least, we don't have to show any stereochemistry. There's no stereochemistry here because carbon number 1 has 2 hydrogens.